Alright, question number 5 asks us to find, 5a I should say, asks us to find the following area corresponding to the region inside the inner loop of cosine 1 minus 1/2. Now that function is a polar function with an inner loop, and we're trying to find the area inside of that. The first thing I'll do in calculating this area is setting our function equal to 0. So cosine of theta minus 1/2 is equal to 0, cosine theta is equal to 1/2. Theta is equal to either negative pi over 3 or pi over 3 to satisfy this relationship. So these are going to be our limits of integration. I jump right in to calculate that area integral. That's 1/2 the integral from negative pi over 3 to pi over 3 of cosine theta minus 1/2 squared. Here I FOIL out the integrand and convert this cosine squared of theta into the half angle identity version, which is 1/2 times 1 plus cosine of 2 theta. It follows that I combine those like terms. We have a 3/4 plus cosine of 2 theta over 2 minus cosine theta. And then I evaluate the indefinite integral and put this vertical bar here with our limits of integration. So we have 1/2 times the quantity 3/4 theta plus 2 theta over 4 minus sine of theta, evaluated from here to here. And then here I have it written out. I could have taken advantage of symmetry and taken the integral 2 times the integral from 0 to pi over 3, and it would have given me the same answer. And that can be seen because when you distribute this negative sign, essentially you get twice of what you had in this first set of parentheses here, which cancels with the 1/2. Essentially the solution is just what's in these parentheses, and it comes out to pi over 4 minus 3 root 3 over 8. Alright, so that's my solution for part A. Part B asks to find the region between the curves r equals 1 plus sine of theta and r equals 1 plus cosine of theta. I have a sketch of those two graphs here. I'll note two things here. There's a large area here, which is very apparent, but there's also a very small area here that I almost missed when calculating that area integral. Second thing I'll mention is that you have this nice symmetry along the line y equals x. So instead of taking 4 integrals, I'm just going to take 2 area integrals, and I'm going to multiply them by 2 to give me the entire area of both regions. And you can see I have my functions set equal to each other to find where they intersect. They intersect at theta is equal to pi over 4 and 5 pi over 4. And then I set them to 0 to find when they intersect with the origin. This first one intersects at negative pi over 2. The second one intersects when theta is equal to pi. So here I have my integrals, very similar to what I had up here. I just FOIL out these integrands and use half angle identities to group like terms and make them integrable. So I'll just jump down here. This is going to be excuse me, 3/2 plus 2 sine theta minus cosine 2 theta. And this is essentially the same thing, but we have a plus cosine 2 theta over 2 instead of a minus cosine 2 theta over 2. Here I take the indefinite integrals and set them up to be evaluated at the endpoints. And through algebra, I cancel out like terms. There's a 1/4 that cancels here and here. And then I add the other like terms, 3 pi over 8 and negative 3 pi over 4. So all in all, that's 9 pi over 8 plus 15 pi over 8, which is 24 pi over 8, minus, this is actually a 12 pi over 8. So that leaves us with 12 pi over 8, or 3 pi over 2, as one of our terms. And then the square root 2's I add together. There's a negative root 2 here and a negative root 2 here. Add those together and you get a negative 2 root 2. And that's my solution here. Again, in the beginning I multiplied both of these integrands, or integrals, by 2 and canceled that value with the factor of 1/2 in front of the both of them to give me that you know, the area of the entire region instead of just these half regions. And that's on the principle of symmetry.